we go. All right. So first, I need to do sections of the notes. Very important concept that's useful in a number of things, not just integration, called Richardson extrapolation. Also known as, and this is actually the term that I was taught a long time ago, back in 1989, extrapolation to the limits. Okay. So the idea is this, that suppose you are approximating something, like, okay, think derivative or integral. And your approximation relies on a spacing h, which certainly derivatives and integrals do. Like when you're using composite rules, for instance. And now, it's important that the approximation behave in such a way that the smaller h you use, the more accurate your approximation is, meaning that f of 0, if you could compute that, would be the exact value. And I'm going to call that A0 just for consistency with the notes. And we'll assume, or suppose we know from proving it earlier, that our approximation has this form. It's equal to the exact value plus, and so the error has this form. That there's some constant times your spacing h raised to the p power. So, so the order of accuracy is p. And then after that leading error term, there's other error terms of order h to the r. And so we have to assume that r is strictly greater than p, so the leading error term has h to the p in it. Okay. So for example, the composite rules from last time, midpoint and composite midpoint trapezoidal rule have order of accuracy 2, so p equals 2. What about Simpson's? How accurate was that? 4. Yeah. Yes, so higher order accurate than midpoint or trapezoid. All right. Now, so the idea behind Richardson extrapolation, and then I'll step through an example with it, is if we go ahead and compute two approximations of f of 0, so using different spacings h. So I have f of h, which has this form. And then I compute a second approximation. So I reduce h by a factor of q. So maybe, like for instance, maybe q is 2. That's what it usually is in examples. So we have the exact value, and then this error term, which would be so this spacing raised to the p power. And then what's left is still going to be proportional to h to the r. Now the constant of proportionality is different, but the point is it's something h to the r. So what I'd like to do is use this extra information, because obviously, okay, well, we're assuming that q is greater than 1 at least. So by reducing h at all, obviously this is a more accurate approximation. But what I'd like to do is use these two approximations together to get an even more accurate approximation. So the idea is if you were to plot your approximations as functions of h. So for instance, you have, okay, so here's your spacing h. You can go ahead and compute approximation that's up here, f of h. And then you cut the spacing, like say, by a factor of 2. So here's h over 2. And we have a second approximation. Okay. So can you use these approximations to get a general idea of where the approximations are going as h decreases? Like maybe you could extrapolate from here to get an idea of what's the exact approximation. Because somewhere here at 0 would be the exact value. This is actually a bad picture. I'm going to adjust it a little bit. Okay. So what is the trend? And of course, the more approximations you compute, so this might be your A0, which is f of 0. Can we use, so basically we're trying to extrapolate to try to make it's not really a guess, but so extrapolation of limits, it's like, well, we could just keep improving the approximation by choosing smaller and smaller h. So you could think of this idea of extrapolating as we're getting that over with, or we're trying to anyway. Okay, so what can we do with this information to more rigorously get a more accurate approximation? The idea is we want to cancel out these error terms. So what I can do is I'm going to rewrite this fraction as h to the p over q to the p. So if I want to get a more accurate approximation by combining these two in such a way that these error terms, so these are my leading error terms, and I'm going to neglect these because those are less significant anyway. So how should I go about combining these two approximations in some way so that my new approximation of A0 doesn't have this kind of error term? I want to get rid of it. How might I go about that? That was weird.
You can combine them in any way.
Yeah.
So you want that whole thing to cancel.
Right.
So you'd have to multiply f of h, right?
Yeah.
By 1 over q to the p.
Yeah. So.
And then subtract them from one another.
Yes.
Aww.
What?
No, that's good.
Okay.
That's what I was thinking of by dividing.
Oh, okay. Yeah.
Yeah.
Yeah. So we just find the right way to combine them.
Yeah.
Okay. So, you're thinking like dividing both sides of the equations or something, or?
No, just go ahead.
She was just using division rather than multiplication by a fraction.
Okay. All right. Okay. Yes, it's an equivalent idea. All right. So now what I can do is go ahead and so now these terms match, so I can subtract. I'll subtract the first equation from the second. So it's this minus this. So now I have 1 over q to the p f of h. No, wrong way. F of h over q minus 1 over q to the p f of h equals, and then I have A0 times 1 minus 1 over q to the p. And then, these will cancel out, and we're neglecting these anyway, so really this is all we have. So now all I have to do is rearrange this to solve for A0. So I have, and of course I can't literally solve for my exact value, wouldn't that be cool? But I'm going to solve for something that's closer to it. So A0 would be f of h over q minus 1 over q to the p f of h all over 1 minus 1 over q to the p. So now I'll just, to simplify this mess, I'm just going to multiply top and bottom by q to the p. So now I'm going to have q to the p f of h over q minus f of h over q to the p minus 1. Now, I could stop there, but I want to write it also in a slightly different way, because if I do a little add subtract trick, because I here have q to the p times this, here I have q to the p minus 1 times this. So, and it's going to be, my board use is about to be kind of weird, but if I go ahead and subtract f of h over q, and then add it back in, and then I can take this term and this term, group those together. Then I can, I have q to the p minus 1 over q to the p minus 1. So, all right. So those of you at home, well, I guess there's only one of you in this case, can get that. But now I will write the, I guess, the preferred form. So really what we can do is we can think of this as taking the more accurate approximation and correcting it. So now I have f of h over q, and I'm going to get the sign right here, plus the difference in the approximations all over q to the p minus 1. Okay. So this is Richardson extrapolation. All right, so this approximation A0 is order h to the r accurate. So you've eliminated the leading error terms. So whatever error terms are next, so the next lowest degree, those step up. Okay. So any sort of approximation that depends on the spacing h, you can use this for derivatives, integrals, especially, and that's what we're most interested in. So now what I'm going to do is illustrate this with an example on for derivatives. And this is a function I whipped out before. This is a silly example of a particularly monstrous function to differentiate, thus using numerical differentiation rules instead. Okay, and I guess I should probably be disturbed by the fact that I could just make something like that up. And I'm sure it could be a lot more diabolical if I wanted to. And what we want is f prime at 0.25. Okay. And we're going to use the center difference rule. So here's our center difference. Now the error is going to be some constant, which I'll call C2 h squared, second order accurate, plus, now what happens is, if you did Taylor series for f of x plus h and f of x minus h and subtract them like this, what you'd find is all the error terms of odd degree cancel out. So, so the next error terms would be even powers of h. And I don't know these constants, C2, C4, C6. I just know from Taylor expansion that that's what the error looks like. And that's not always as easy to work out, but in this case you're just subtracting two Taylor series with symmetric equal spacing, so that's what happens in this case. So if I do some extrapolation to eliminate this error term, this would be the next one. And the nice thing about knowing this, that I have even powers of h, that lets me apply extrapolation multiple times to get more accuracy. Okay, so what I'm going to do is like make a table of sorts. To see what happens. Okay, so the first thing I do is I need to use this rule to compute two approximations. And so my notation, I compute n1 of h. So I'm using my center difference with spacing h. And all I want to really show you here, because the numbers themselves are going to be kind of meaningless, what we want to see is the error. What happens to the error as we extrapolate? So at least we can compute the exact value to compare against to see how well this works. So, and I'll use a spacing of 0.01. And the error is roughly 0.003. So not bad. And then I do it again with half a spacing, so 0.005. Now this is second order accurate rule, so the error should decrease by about a factor of 4. And so the error in this case is 0.00077. And that is roughly a quarter. Okay, but we want to see if we get even more accuracy just through a little bit of work to by combining these approximations using Richardson extrapolation. So, what?
0.005.
Oh, yeah, it's kind of bad writing. Okay. All right. So these are my initial approximations, and now I can use these two to extrapolate to compute a new approximation that I'll call n2 of h. So the subscript here is like layer of extrapolation. These are my first approximations. Here's my first extrapolation. And for this I'll use this formula. So this would be n1 of h over 2, the more accurate approximation, plus the difference of them over 2 squared minus 1. So divided by 3 in this case, because I'm cutting h by a factor of 2, that's what the base is for, and the exponent is the order of accuracy of approximation. This is second order accurate. So what happens when I perform just a single approximation? Did I not write down the error? Oh my god, what's wrong with me? Sheesh.
For the 4? For the h over 4?
No, I haven't got to that yet. So n2 of h. Yeah, because for later ones I have it. I just omitted this one. Okay, so, alright, here's what I'll do. Okay, because somewhere here I think I have the... Oh, okay, I do have the exact value. Okay, so in this case the error is, okay, so how many decimals? This is awful. Okay, so I have, what am I doing? This is my calculator. All right, so I have, all right, so the exact, okay, minus the approximation, which is, okay, so this is 0.0000026. Okay, so here we had, so we're at 10 to the minus 4, but now we're at 10 to the minus 6. So it went down by a lot. So that's quite nice. And after doing this, whatever it takes to compute these approximations, like derivatives, there's not much work involved. These could also be integrals, which would take a lot more work. But then, no matter what, you're just doing hardly any operations at all. A subtract, a divide, and an add, bam, done. And already you've wiped out that error. Okay, so any questions about this extrapolation before I do more extrapolation?
How is that P equal to 2?
I just chose that. So the point is, you just choose what factor to reduce h by. And 2 is a pretty common.
It's Q, right? Not P. Q.
Oh,
Wait.
I'm sorry, we're asking about P or Q?
I mean, I asked about P.
Oh, yeah, because we know the order of accuracy of this by looking at Taylor series expansion. And well, when I cover differentiation, it was done there. Okay. Yeah. So, actually, yeah, from Taylor series expansion of these is you get this form of the error. Okay. So I guess I need to mind my P's and Q's. Okay. All right. Any other question? All right. Now, let's get greedy and reduce the error even more. But in order to do that, I need I'd like to have something to extrapolate against this with, but I don't. So to do that, I need another approximation. So I can go with h over 4. So h in this case is going to be 0.0025. And the error is going to be like roughly 1/4 of this. So 0.00019. So now I extrapolate between these two. So didn't take much extra work. So I have n2 of h over 2 combining the h over 2 and h over 4 approximations. Oh, this is n1 up here. n1 of h over 4 minus n1 of h over 2 over 3. And the error in this case is, now, what we get is 1.7 times, okay, so 0.00000017. So the reduction in the error was actually pretty substantial. So the error reduced by a factor of roughly 15. Now, because the thing is, we've canceled out this error term, so these approximations are 4th order accurate. So if you reduce h by 2, the error should reduce by a factor of roughly 16. But I hardly use any decimal places here, so 15, that's close enough. Okay, so now we're doing quite well here. But now I have 2 approximations of this kind. I can extrapolate between these two and reduce the area even more. So I have n3 of h, which is n2 of h over 2, plus the difference in the 2 approximations, But now I have to think, what's divide by? If we go back up here, I don't divide by 3 now. So keep in mind, what is the P and the Q in this case? Well, the Q is still 2. I'm always cutting the H in half. But what's the P this time?
Is it 8? I mean, not 8, is it 4?
It's 4. Yeah, because I got rid of this error term already. This is the next one that steps up. So it's 2 to the 4 minus 1. I need to divide by 15. So, yes, so these are, so here, my order of accuracy is 2, P equals 2. Here is P equals 4. Now, this extrapolation, I should get P equals 6 for order of accuracy. So I go ahead and compute that, perform that extrapolation, and the error turns out to be, okay, 1, 2, 4, 5, 6, 7, 8, 9. Yeah, so 1.8 times 10 to the minus 10. So shockingly accurate, considering how little work was done. The only function evaluations we needed were, well, 6 altogether, 2 for each of these. And then we just extrapolated past that point. Because the main work is a function evaluations, and that's what we try to minimize. And yeah, using a pretty small spacing, not terribly small, we can still get such a high order accurate approximation. And we see that from each step, it accomplished a lot. So that's quite nice. Okay. So any questions about all this extrapolation? And the things unfortunate about methods like this, like, it'd be so nice if this really worked all the time. What we're going to find is, you try this on any approximation with a spacing h, extrapolation of this kind does not always yield this much of a benefit. It depends on the example. But yeah, when it does work, it works really well. And for integration, the benefit is quite substantial because it takes a lot more work to produce these initial approximations because you're evaluating your functions many times over so many subintervals. But then the amount of work here is very small by comparison. So you get a lot of bang for your buck if you're using this as integrals rather than derivatives. Okay. Now, so now what I'd like to do is show why it was relatively easy in this case to apply this to derivatives, and then see what we can do to try to apply this to integrals. Okay, so I'm going to carry out real quick what is the process that I used here to even get this form of the error. How do I know that? I mean, I said it in words, but I'll just write it out because it doesn't take much. If you look at f of x plus h and f of x minus h, with x plus f prime of x h plus 1/2 f double prime x h squared. Here we have minus f prime of x h. So it really is replacing h by minus h in the second case. Term. Okay, I need to go out a couple more terms. So fourth derivative. fifth derivative. Okay, so what will happen is if I go ahead and subtract these and then divide by 2h, then all of the terms corresponding to even powers of h are going to cancel. And then the terms of odd powers of h are going to add together. So what I'm going to get is f prime of x, which is what I'm after, my approximation. And then I'm going to get h squared over 3 f double prime of x. And then I'll have 1/60th h to the 4th. Fifth, wait, oh, this is third derivative over here. And then fifth derivative of x. And so on. So now, this is how I know the form of the error. That I have a constant times h squared, and I can actually say what that constant is, plus another constant times h to the 4th, and then it would just continue from that point on. So that way, I have to know the form of the error if I want to, not just the leading term, but later terms, if I want to apply extrapolation repeatedly. If I know the leading term, I can apply it once, to like, in this case, improve to a 4-4 approximation. But if I don't know about this, I can't keep going. So in this case, it worked out pretty nicely. Differentiation rules, you can get expansions of the error that allow you to apply extrapolation as many times as you want. So the problem is, what about integration? I don't have that. So as an example, the composite trapezoidal rule, what we know is that the exact integral is equal to my composite trapezoidal rule approximation plus an error, and the error, I have a formula for that, it's minus h squared over 12 b minus a times the second derivative at an unknown point in AB. So if I wanted to, I could apply extrapolation one time, but not past that point. And besides that, there's another problem with applying extrapolation even once, and that is this. I'm evaluating the second derivative at an unknown point between A and B. And if I compute a trapezoidal rule approximation with spacing h, and then do it again with h over 2, how do I know if it's going to be the same? I don't. So the error terms might not really cancel. So, whereas derivatives, it's not a problem. We know exactly what the constant is. It's higher derivatives at the very same point. Now, okay, I may not need to know the value of a constant, but the point is, this right here, these constants that multiply my powers of h, are independent of h. And I guess they are independent of h factorial. Couldn't resist.
Why did, like where you have h squared over 3 times the third derivative?
Yeah.
Okay, why is it h squared and not h cubed?
Oh, because I divide by h.
Oh, okay.
Yeah.
So that's after having
Yeah.
h.
Yes. Yeah, because if I just do the subtraction, I get f prime of x times 2h. I need to get rid of it.
Right. Okay.
All right. So now I have this wonderful extrapolation technique that I can't use for integrals. and that pisses me off. So that's how innovation happens. Someone gets pissed off about something, and they figure out a way to work it out. What?
Work around it.
Yes. Yeah. So what?
The divide by 2h, right?
Yeah.
So shouldn't 1 by 6 plus 1 by 6, that's 2 by 6. Divide by 2h should give you 6 by 6, right?
Yeah. Yeah. Add them together. But yes. Okay.
Oh, now they should do whatever 20 then.
Yeah. Okay. Yeah. Totally forgot about that. Oh, good catch.
Yeah, I was dazed for a minute and I was like, why do you do that?
Well, that reminds me. Actually, does anyone happen to have the textbook on them?
Yeah.
Okay. Because my difficulty was sometimes in these differentiation rules, I remember the error formulas, but that didn't happen in this case. So I thought, well, I'll just assume that when I work it out here in board, that it'll be the correct thing. And I want to see if this actually has the error. Except, well, this doesn't have the actual formula. Okay. Oh, never mind. Wow. What an overly terse presentation. However, if I look at my notes, I know it's in there, but it's not the notes I have with me today. Yeah, because what I have on the board now should be correct. But I just want to make absolute certain. Okay. So center difference. Okay, yeah, F triple prime over 6. Okay, yep. Alrighty. Yes, yeah, because then if I remembered that, then I could have caught this soon myself, but okay. So what I want to try to do is get a more detailed error formula. Like not just this leading term as proportional to h squared, but what are the terms after that? And maybe then I can apply extrapolation to composite trapezoidal rule as well and get more accurate approximations to integrals as well as derivatives. And I'm not sure if I can finish this in time, but I'll see what I can do. So this is called this leads to what is called the Euler Maclaurin expansion. Of course, the name Maclaurin ring a bell from Taylor expansions that are centered at 0 are called Maclaurin series. I wonder how Maclaurin horned in on that and scooped up that center equals 0 case for himself. Quite a coup there. Okay. So, so to study the error to trapezoidal rule in a little more detail. Okay. So I'm going to assume my integrand g of t is differentiable, where I h right out in full, on -1 to 1, just so I can work with derivatives. So then, here's what I can do. If I work out the integral of g on -1 to 1, using integration by parts. So this would have to be the u, and this would have to be the dv. So what I get is u times v, so that's t g of t, at the limits minus 1 and 1, minus integral of v, which is t, times du, which is g prime of t. So t g prime of t. Okay. Now something interesting happens when when I plug in the limits here. So I get, when I plug in the first limit, I get g of t, and then I have minus 1, so a plus, it's g of 1, plus g of minus 1, then I have this. Okay. Now, who cares? Well, it turns out this is what we would get if we used the basic trapezoidal rule. So just one trapezoid, because we're evaluating at the endpoints, and then you multiply that by the width of the interval, which is 2, divided by 2. So we just get this. So if that's the case, here's my exact integral. Here's my basic trapezoidal rule approximation. That's my error. So now I have another way of representing the error, and maybe I can use that as a starting point to get something, get a form of the error that can be used for extrapolation. Okay. So here's what I can do is I want to apply integration by parts to this now. So if I have minus, well, I'll leave it at minus, let's focus on the integral. That's on 1 t g prime of t. Okay. Well, let's see. Actually, it looks like, dang it. All right, I need to leave a minus in there, so I'll put minus t. Okay. Now, to apply integration of parts, I need to choose my u and my dv. Now, the funny thing is, I often tell people if you're doing integration by parts, if there's something that's already differentiated, use that as a dv. But that would just bring us back to where we started. So we're not going to do that. So I'm actually going to call this my u, g prime of t, and then this together is my dv. So, well, in that case, what should my v become?
T squared is root 2.
Yeah, and don't forget the minus. So yeah, so minus t squared over 2. Yeah, so, and so now we can have g prime of t times the integral minus t squared over 2 plus some constant of integration, which I don't know what I want it to be yet, evaluate at minus 1 to 1. And then I can, so then I'll have minus, and then I have v, which is minus t squared over 2 plus whatever constant, times du, which is g double prime of t, dt. So now I can work out what this is. Okay. So this gives me, you think of this as a leading error term. And then there's more error terms in here. And the thing is, I can keep doing this as long as I know the derivatives of g exist. I can keep doing this as many times as I want. And what happens is whatever polynomial, is that something I should care about? No. Whatever polynomial I have here, if I apply integration by parts, I'm going to anti-differentiate this again. So we're going to keep getting higher and higher degree polynomials. So cutting to the chase here, what do I actually get if I apply integration by parts a zillion times? So what I get is something of this form. Okay. All right, so my original integral is equal to my, so minus my basic trapezoidal rule approximation equals my error. So everything I put on the right side of the equals is the error. And my boundary terms from integration by parts would be, okay, so Q2 of t g prime, which comes from here. I'm just labeling it differently. Okay, minus Q3 g double prime, if I were to do integration by parts on that integral there, plus, and you just keep going. There's going to be alternating signs because of the minus and integration by parts formula, all the way down to, okay, so if I keep going, 2k minus 1 times. So that's how many times I apply integration by parts. What I'm going to get is a sequence of polynomials, q2, q3, and so forth, all the way up to q sub 2k, times the 2k minus 1 derivative, all evaluated at minus 1 to 1. So these are my boundary
Are
terms.
these Q's or G's?
Yeah.
Oh God, not again.
The
The
ones that are
subscript-
straight are
The subscripts are Q's and the derivatives are
The
G's.
G's have an actual hook in them.
Okay. Well, my Q's have hooks, you know, because I can't. Q's and G's. Always representing. Okay.
Okay.
So is that a G?
Q.
This happened to me, something like this.
Change the wrong one to a Q.
Something like this happened to me at Stanford, where I was giving a substitute for Marco Garrison, and I gave a lecture about the QR factorization. Oh, I'm sorry, you know about that now. Okay. And describing it on a column by column basis. So I'm dealing with columns of A, like AI, and columns of Q, QI. And when I got the notes from Margot about what to present, she was using different letters. Even though A equals QR, that is the standard notation for this, for what we're doing, is Gram-Schmidt orthogonalization. So I thought, well, I don't know why she did that. I'm going to stick with my A's and Q's. And after I get to the whole end of presentation of this topic, it's when I found out why she switched letters. Because then the student said exactly the same thing you did about not being able to tell A's from Q's. And I got so frustrated, I literally threw chalk up in the air. It's like, and it is a huge auditorium, so it actually could go somewhere. And like, what? Then I basically tried to like fix it up and that sort of thing. And it's like, oh God, this nightmare will never end. So thank you for that. Now I know that there are two letters not to use in combination with Q. And this is straight out of a textbook, so it's their fault. At least I can blame them. Okay. Minus the integral that's left over after all the integration by parts. And actually, I don't know why the textbook used G instead of F, because normally F is used for the integrand. That doesn't look anything like a Q. So, all right. Q 2k, and then 2k's derivative. I guess I better exaggerate my hooks. Okay, I have to see this in your notes just out of morbid curiosity.
Well, I just scratched over them really dark, so you can't see
Oh.
my hooks anymore.
Oh, okay. No, well, that's the first time I used the Q's, so okay. All right. So, See, this is what they don't tell you when you're
Yeah,
learning
the
how to
other
teach.
day you were like, are those Q's or G's? Because I always learn, I don't know, I get confused.
Okay. Oh, well, this is gonna be fun. Okay, so
How do you do a Q?
The opposite of a G.
Oh, okay, cool. Okay. Sorry, go ahead.
also, if someone's dyslexic, it's really bad. But yeah. Okay.
Yeah, and I'm like, yeah.
Okay. All right. So, okay. Now, what are these polynomials? So these polynomials. I define as follows. I define Q1 to be equal to minus t that we saw from a first integration by parts. And then each successive polynomial is the antiderivative of a previous one. So for instance, like you have a minus t squared over 2 and so forth. But we have to keep in mind there has to be a constant of integration. Now here's the thing. Q1 is an odd function. What happens when you integrate an odd function?
Gonna change signs.
It will be even.
Yes, it changes parity. Yes, so odd function, when you differentiate or integrate, becomes an even function. Yeah, okay. But the thing is, we have to be careful about this. We need to choose the constants of integration carefully in order to make sure that, so QR, by choosing your plus C's correctly, is odd if R is odd, and it's an even function if R is even. Basically what that means is, in fact, the first time around I take minus t and I get minus t squared over 2. In that case, it doesn't really matter so much what I choose the constant integration to be. But if I integrate that, well, or does it? Okay, because that's, okay, that's not going to matter. But the next time around, when I get a cubic, and then that constant, whenever I chose it, becomes a linear term, that's an odd function as long as I choose the next constant of integration. Like for Q3, I have to choose a plus c to be 0 for it to be an odd function. Because when you have an odd function, you must have f of 0 equals 0. So basically, you're choosing every other constant of integration must be 0. Or I guess you might as well choose them to be 0 just about all the time. Okay. Oh, but there's more. So you not only need this to be true, but you also want this property to be true. You want QR of minus 1 and QR of 1 to equal 0 if R is odd. So that is a more stringent condition. Again, by choosing a plus c's, you can make that happen, but again, you have to be careful about it. So that's really the more limiting thing about making that happen. So the reason why we want to do that, so that will cause, because you're going to plug in minus 1 and 1 into each of these. So that means we can eliminate any of the odd numbered ones. Okay. So then what happens? And actually, these have a name because these were actually featured in an assignment that way back that Dr. Kolobal gave in Honors Cal 2 of all places. A bit too advanced for them, I think. But these are called I think they're called Bernstein. Wait, no, they're not. Bernoulli polynomials. I'm pretty sure. We'll just go with that. Okay. It was some B name. I was thinking Bernstein polynomials, but that's a different family that Dr. Kolobal also happened to use in his research. So, okay. Now, so when we satisfy these conditions, so we can get certain terms to drop out, the error now has this form. How am I doing on time? Ooh, okay. Wait, how much further do I need to go? Oh, okay, not much further, so it'll be fine. So now you have k terms that have the even Bernoulli polynomials evaluated at 1, because the thing is, I'm plugging in 1 and minus 1 into these polynomials, but if these are even functions, the values at minus 1 and 1 are the same, so I can factor it out. So now I'll have odd order derivatives of g evaluated at 1 and minus 1. Okay. So I have all those terms added up, minus this integral, this one here. Well, yeah, q2k of t times a 2k derivative of g. Okay. Now, the thing is, this is the error for the basic trapezoidal rule. For a generic function g on minus 1 to 1. But now I want to generalize, and I believe this is why the textbook offered use g, because now I want to go back to a general interval ab with a function f of x, and apply not just the basic trapezoidal rule, but the composite trapezoidal rule, in which we'd have all these error terms added together. But here's the nice thing. Suppose I do this on each subinterval in a composite trapezoidal rule, and I'm going to be adding a bunch of these together corresponding to all my trapezoids. Now, in the trapezoidal rule, the composite one, we had certain f values shared between trapezoids, and those terms added together. But now they're being subtracted. So what's going to happen now? For points shared between trapezoids. Because I'll have this for my first trapezoid.
The constant constants were 2 because we added those
Right,
2.
yeah.
Right now, there is a change in constant, maybe from 2 to 1.
Yeah, but so for instance, you might have like this at x1 and this at x0, and then at x2 and x1, x3, x2. And because they're subtracted instead of added, what's going to happen this time?
All the inside terms are just gonna simplify,
In what way? Simplify how?
like cancel.
Yes.
0.
Yes. They'll be the simplest thing imaginable. 0.
You just
Yeah.
put boundaries on the same.
Yeah, so now the only terms left will be the boundary terms. So that works out beautifully. So now I have this expression for the error in the composite trapezoidal rule. Okay. All right. Yeah, so instead of 1 plus 1 being 2, you have 1 minus 1 giving you 0. So you have, for a composite, trapezoidal rule. Okay. So we have integral. So now I can stop using g's. All right. So exact integral of f is equal to what you get from a composite trapezoidal rule. So all these interior values are multiplied by 2. And then the boundary values are not. Okay, that's the approximation. And then the error has this form. So it's that error added up, but you have all these interior things canceling. So I have a sum of some constant, c sub r, h to the 2r, because before we were in an interval of width 2, but now we have an interval of width h, so that has to be taken into account, times odd order derivatives of f evaluated at your endpoints and subtracted. Okay. Minus h over 2 to the 2k integral. And this one has, you're adding integrals over subintervals. Okay, it's kind of weird here to have an integral dx, but now I have a t in there. But I could define t. So this t is equal to minus 1 plus 2h x minus xi minus 1. Okay, so basically you're making like a u substitution in a way. But you're using a different u substitution on each subinterval to map your subinterval to minus 1 to 1. Okay. Now, I need to define these constants. These constants are equal to my q's evaluated at t equals 1 over 2 to the 2r. Because what happens is, before I was differentiating g on the interval minus 1 to 1. Now I'm differentiating f. So really what's happening is the change of variable from minus 1 to 1 to a generic interval of width h is introducing this factor of powers of h. And notice they're all even powers because we got those odd order terms to cancel. I should mention that these constants are also equal to b2r over 2r factorial minus. And the b's are called Bernoulli numbers. That come from the values of the Bernoulli polynomials. Okay. Now, this whole thing is called the Euler-Maclaurin expansion. Okay. Now, why is this so nice? Because it gives us a multi-term representation of the error in the composite trapezoidal rule. It proves that the error of the trapezoidal rule, which we already knew was proportional to h squared, is actually a sum of terms of even powers of h. So if we did extrapolation with the composite trapezoidal rule to wipe out the h squared error term, the next one coming up will be h to the 4. And we can keep going, h to the 6, h to the 8, and so on. Also, what's multiplying the powers of h? Something fixed. These constants, based on the Bernoulli polynomials, times these derivatives of f at a and b, independent of h. So if we keep extrapolating, we have this, we are assuming the error is a constant times the power of h. And now we know it really is a constant. So that's important. So it helps extrapolation actually work. Provided that these derivatives actually exist on the interval. Now, so for instance, for a function like square root of x, this is not going to work because your derivatives are going to, if x equals 0 is an endpoint, because your derivatives are not defined there. So it doesn't always work, but at least we have something under certain assumptions on f that does work. Okay. So what I'm going to cover starting next time, okay, still have a little time left. Next time is how we combine Richardson extrapolation with the Euler-Maclaurin expansion and composite trapezoidal rule to get a new technique called Romberg integration. And what I did earlier with derivatives, I could do with integrals. So I'll get into that next time. But the last comment I want to make now about this Euler-Maclaurin expansion is something else that it gives us. What if f is periodic and is also differentiable? So you assume that you can take as many derivatives as you want. And not just any periodic function, a period fits into the interval AB. So maybe it's b minus a periodic, or maybe it's periodic of a multiple of b minus a. Well, what happens if you differentiate a periodic function? What do you know about the derivative? Like, for instance, take sine or cosine. It's still periodic. So, if f is periodic, and I take these derivatives, what happens to these terms here? Assuming it's at least continuous and all that.
Wait, what? Which term?
If f is periodic, then what do we know about the values at a and b?
It should be the same.
Yes. So what happens to these terms here?
We go back to the composite trapezoidal rule again. The first formula.
Well, yeah, so the point is that this goes away.
No, I mean, I just thought that term will be double. I mean, we'll have two of that term.
Of this? These would add together.
Oh yes.
Yeah, but that's true.
So
But
it's not right.
yeah, so that's not the interesting part. Okay, but yeah, these will cancel in this case. And the thing is, here I've carried this integration by parts out a certain number of times, k times. But if I could differentiate as much as I want, then I could have as many of these terms as I want. That still cancel. So it's almost like, I wouldn't say the error is zero necessarily. But what happens is the composite trapezoidal rule goes to zero with exponential order. So the composite trapezoidal rule, normally second order accurate, suddenly becomes exponentially convergent, meaning that the error goes to zero faster than any power of h. So it no longer has polynomial order, it's to a new, this is also called like superconvergence, which you really love to have and don't see very often. I'd love to develop a superconvergent method of any kind. So what you would see is just lightning fast convergence as h goes to zero. And that's why for applications involving periodic functions, and those are still very important in certain applications like solving solving equations on circular domains, things like that, that the composite trapezoidal rule is actually the best integration rule to use for those situations. Whereas in many other situations, it's dog meat. But in this case, it's utterly fantastic. So it's like optimized. So,
It is amazing.
yeah. So okay. Yep. I guess I'm out of time. So technically, I did have 1 minute left. So you shouldn't pack up like that. But whatever. Okay. But everything is covered. So now we'll pick up with this.